Hi, everybody. Welcome. I'm Viveca. I'm the Executive Director of the Law, Ethics, and Animals program here at the Law School, and we are so thrilled to have Matthew Hayek as our guest speaker today. Before I introduce Matthew, a few logistical notes. Please be aware that this event is being recorded. It'll be on YouTube later if you want to relive it. Please help yourself to lunch in the back if you haven't already gotten it. It looks like it's going fast, but all the food is vegan, including the cookies. There will be time for a Q&A after Matthew's talk, so we'll ask that you please hold your questions for him until the end. And then lastly, thank you very much to our co-sponsors for this event, which include the Yale Animal Law Society, the Yale Environmental Law Association, and the Yale Sustainable Food Program. So with that, I'm delighted to get to introduce you to Dr. Matthew Hayek. Dr. Hayek is an environmental scientist and assistant professor in New York University's Department of Environmental Studies. His scientific research quantifies the environmental impacts of our food system with a specific focus on greenhouse gases like methane and nitrous oxide. And he's also an expert in land use changes, including deforestation. His research uses environmental and statistical analyses to try to clarify the contributions of the food system and food system policies and to move them towards mitigating emissions in line with national and international climate targets. He received his PhD in environmental science and engineering from Harvard, which was followed by a postdoc at Harvard Law School. He's also an affiliated member in NYU Center for Data Science and the NYU Wild Animal Welfare Program. So we are so thrilled to have him today. We have the pleasure of collaborating with Matthew fairly frequently through our program over the years, and he's a real rising star in his field, and we're so delighted to have him. So please join me in welcoming him.
Thank you so much for the warm introduction, Viveca, as well as Caroline, Lori, who's not here today and out sick, and just the entire Yale LEAP program and all of its affiliates. It's a wonderful community to be integrated in and a part of and occasionally collaborate with, and hopefully we can do more in the future. So today I want to talk about who the climate polluters are in our food system. And today this is a conversation that's an open conversation about the countries, regions, operations, and sectors that are responsible for many of our greenhouse gases. Not a majority, of course. That's fossil fuels for energy, transportation, and manufacturing, but a significant enough proportion of them that it might prevent us from reaching some of our climate goals and some of our climate targets. And the goal today is to also demystify the science and how we come to some of these decisions, and having a discourse that helps us understand some of the obstruction that might get in the way of having that scientific conversation in the spirit of having honest, frank, and open discussions, finally beginning to address this problem of greenhouse gas emissions from food systems. So I'd like to start, before talking about food systems, with what brought me to this problem or this sector of emissions of the food system. In my PhD, I worked on atmospheric monitoring of CO2 from a tall tower above an old-growth Amazon rainforest, to measure the breaths of photosynthesis into and respiration out of that forest, to better understand how the forests were interacting with, moderating, and responding to global warming. And we did that right here in this dark, lush green patch called the Tapajos National Forest, which is almost the size of the state of Delaware. But all around us were these highways and deforestation scars coming off of the highway that boxed in the protected site between that north-south highway, the Santarém-Quiaba Highway, and the neighboring Tapajos River. And 95% of this deforestation is due to the production and rising production of inexpensive beef. So much of it that this state, Pará, in the eastern Brazilian Amazon, has the most rapid rate of recent deforestation in the entire region. And this really confronted me while I was doing this research where we were trying to understand the response of these intact old-growth Amazon forests of anthropogenic climate change in 30 to 100 years' time as droughts increase. They were disappearing across the highway from us yesterday. So this brought me to doing some background research in environmental science and continuing to stay up on the literature about food systems climate impacts that I'll address in part one. In part two, I'm going to talk more about our own research of testing our own hypothesis about whether and how much agriculture could contribute to being a climate mitigation solution on the land that we currently grow food on, and with a particular focus on animal-sourced food, which I'll describe as a major proportion of that land use. In part 3, I'm going to talk more about our research in methane and trying to unmask or uncover some of those impacts between production regions, between varying levels of intensity and production styles, and different metrics for accounting for those methane emissions that are beginning to be adopted. And finally, I'm going to discuss what I'm calling the tricky business of emissions accountability. Business kind of capitalized there, a bit tongue-in-cheek, because there's currently a lot getting in the way of having transparent discussions about where those emissions are coming from, how meaningful they are, and what needs to be done to address them. So first, starting on this background. The widest view that I can give you right now is that agriculture is responsible for about 1/5 to even more than 1/4 of global greenhouse gas emissions. And if we tack on the mostly fossil fuel-powered agri-food supply chains, things like transport, fertilizer, and pesticide manufacture, refrigeration, et cetera, that adds another about 4 to 10% of overall emissions. And focusing back on agriculture, agriculture alone is responsible for major emissions, all the top 3 greenhouse gases, including carbon dioxide, which from the food system predominantly comes from clearing land to make room for more agriculture, in particular lately in tropical countries where entire dense tropical forests are being deforested to make way for more food production, as well as some of the agricultural machinery and the infrastructure associated with supply chains. Methane, that predominantly comes from cattle belches, but also how we store manure. A lot of it does come from rice fields, and it's not that much per acre, but it tends to be a lot when we add up major staple crop production all over the world, as well as some of the extraction and refining of fossil fuels, and even our food waste and disposal. Methane is generated from that. And lastly, there's nitrous oxide, which I like to call the forgotten greenhouse gas, or the other greenhouse gas. It's the 3rd most important greenhouse gas when adjusted for global warming, and it essentially comes from all nitrogen-containing compounds in the food system. Predominantly, that is manure, as well as fertilizers, but some of it even comes from legumes that work symbiotically with bacteria in the soil to produce more reactive nitrogen that they can use to fertilize themselves. Legumes have always produced a little bit of nitrous oxide, but of course we're planting more crops, leguminous crops and otherwise, than we ever have in the past. And importantly, we don't just add these up ton for ton because it's not like for like. Each one of these greenhouse gases lasts different periods of time in the atmosphere and has different amounts of warming on a gram for gram or ton for ton basis. So we adjust the weight of each one of those 3 by their global warming potential in this case, but we'll nuance this later using GWP 100, so an average or an integral of their warming over 100 years, which creates one rough unit of comparison called CO2 equivalent. This helps us compare the apples of methane and nitrous oxide to the oranges of carbon dioxide. And when we look at one of the, more than half a dozen studies listed in the first slide, but a major one, a major meta-analysis of where emissions are coming from in the food system. This study found about 26% of the food system. It took a conservative view of how much emissions are coming from supply chains, but we can see that a lot of the emissions are coming from livestock directly, but also that crop production entails growing a lot of crops for animal feed, and land use change, the majority of that land use change, mainly deforestation, is devoted to making room for more animals. And this brings us to our first point, which is that animal agriculture and animal-sourced food requires a disproportionate amount of emissions, about 60% of the global total, or 8 gigatons of CO2 equivalent, which is about 15% of global overall emissions. And this is accounting for the fact that, and this is rather disproportionate in light of the fact that animal agriculture, animal-sourced foods only account for 1/5 of global calories and 1/3 of global protein. The reason that these impacts seem somewhat disproportionate has to do with trophic efficiency. You have to feed animals something to get food from their flesh and byproducts. In fact, it takes around, even in a high-income country like the United States, where animal agriculture is relatively efficient compared to the rest of the world, it takes about 9 calories of grain to produce 1 calorie of chicken, and 40 calories of feed to produce 1 calorie of beef. Even if you only look at the edible feed crops that we feed cattle, it still takes about 25 calories of crops to get 1 calorie of beef in return. And what this amounts to also is different greenhouse gas emissions, vastly different ones, depending on what food is being produced and consumed. With many animal-sourced foods at the top, this is on a kilogram for kilogram basis, not adjusting for protein, so some of these have, of course, more water in them than others. But beef, cheese, pork, as well as some tropical commodities associated with deforestation like chocolate and coffee, are towards the top of this list, with plant sources of food, in particular plant sources of protein, all the way at the bottom. Each one of these commodities, in turn, is divided up by different stages of its production, from land use change in green and farm-level emissions like methane belches and methane coming from rice paddy on the farm in brown, to transport in the red. An interesting side point of this figure is that all transport emissions are only about 4% of agri-food system GHGs total, going up to 11% in high-income industrialized countries like the United States. Overall, it seems to matter far more what foods we're eating than where those foods are coming from. So if local food isn't necessarily a greenhouse gas mitigation solution, what else is? Well, multiple scenario analyses have been done even within the past few years, and this is one scenario analysis comparing different mitigation measures in shorter bars to business as usual diets out to the year 2100, the cumulative emissions over the next about 80 years in the black bar. And what you can see from that black bar is that business as usual growth in food systems alone could take us up to and even past 2 degrees of warming, even if we were to cut out our all of our fossil fuel emissions for energy, transportation, and manufacturing tomorrow. Food systems alone, even though they only contribute 1/4 to 1/3 of greenhouse gas emissions, are enough to take us past the targets that we need to reach. So what can we do? Well, there are 2 main categories of things that they tested, as well as a half a dozen other studies. First of all, we can make production more efficient, growing crop yields at higher yields per area, more crop in an acre in the dark blue, or in the light blue, we can produce animal agriculture at a higher efficiency, feeding animals a little less to get a little bit more meat and dairy in return. But we can also change the total amount that we consume and thereby produce, especially of emissions and land exhaustive animal-sourced food. So we can eat a healthier amount of calories, we can waste less of it, and we can shift to plant-rich diets and get most of our protein from plants rather than animal-sourced foods, particularly in high-income countries and in urban areas in middle-income countries. And what this amounts to is the same thing that you see across multiple other scenario analyses. This from the World Resource Institute, rather than looking at cumulative 80-year-long emissions, just looking at the emissions in one particular year, the year 2050, where you find that production efficiency and consumption shifts are both needed in order to take us to the levels of greenhouse gas mitigation that we need to see in order to reach our climate targets. But there's more that we can do besides just making food production more efficient and consuming less. What about all this news of feeding seaweed to cattle to get them to belch less? Well, we commented this in the year 2021, and the story has not changed much since then. These are really interesting prototypes that offer promising reduction at a pilot scale, more akin to a grain-rich feedlot where cows don't mind eating small amounts of these bitter additives. But when you put it on a farm and consider that on most farms cattle spend 2/3 of their life grazing, it's only in the last third that they're fed these crop-rich diets more akin to Pop-Tarts and Doritos for us, that they'll tolerate consuming some of these bitter seaweed products. So what might sound on paper like a 90% reduction, in effect within the whole lifespan of a cow and all the beef and dairy that's being produced, is only akin to a 9% reduction. Don't just take our word for it. There was a major study done in 2022, in part done by Claudia Arendt of the International Livestock Research Institute, as well as my current postdoctoral researcher, Shelby McClelland, that found that even under the most optimistic scenarios that they could muster of improving efficiency and using this mitigation technology, mitigation tech won't meet our climate targets even to the year 2030, let alone the year 2050, because it is massively outweighed by the projected growth in animal demand. Meat and dairy reduction is also necessary. And while some regions like Europe on the bottom can meet most of their goals by the year 2050, this certainly can't happen in areas that are rapidly increasing their meat consumption like East and Southeast Asia and Sub-Saharan Africa, where the consumption is taking the overall methane emission trends in the opposite direction. By 2050, no regions, including Europe, the United States, or Australia, or any of the rapidly economically developing world, can meet further methane emissions reduction targets of about half of their methane being reduced by the year 2050. So none of these mitigation scenarios, on the other hand, have even taken into account what else we could do with all the land that's currently used to grow animals. All of those scenarios only included current rates of deforestation. Well, why is that important? Well, in the United States, we use over 40% of our land to grow food. And the vast majority of that is the food that we feed to animals and the grass that we graze cattle on, rather than the food we eat, which is only akin to the size of a couple Midwestern states, Illinois and Indiana. More than twice that is animal feed and biofuel, and 4 times that, or 4, 5, 6 times that, around 30% of the country, is cattle pasture. This bears out on the global stage too, where even though all of the built-up area across the entire Earth, all the highways, warehouses, suburbs, farmhouses, and urban centers are about the size of the country of Libya, the amount of land that we use to grow livestock is more than a quarter of the Earth, or the entire set of the Americas. And while granted, a lot of, I've heard a lot of people say, well, most of that land we couldn't be doing much other with than grazing livestock. It's natural grassland, it's shrubby desert where you couldn't necessarily plant crops, at least without irrigating it a ton. However, about 10 million square miles of this 30 to 40 million are areas that have historically replaced humid forests to now grow food. 10 million square kilometers is equivalent to the size of Australia and India combined. And these areas would be lush, humid forests that we could regrow into these carbon-rich ecosystems if we weren't regrowing feed crops, currently growing feed crops for pasture and crops to feed pigs, chickens, cattle, and sheep. Not only pasture production in Brazil, which requires the land to be kept clear of encroaching forests, but also hay and silage production in dairy country in upstate New York. We mapped all the areas where production occurs for animal feed, minus the land that you would need to take to produce protein-rich crops as replacement for those animal products, and multiplied that by all the terrestrial carbon that would be there if it was instead undisturbed by human planting and activity. So ultimately, what we have here is what we've called the carbon opportunity cost of animal agriculture, the mitigation potential of that land if we were to drastically reduce its size by higher yields and shifts to better diets. It was already known, and it's already been the case, the IPCC reported this in 2019, that reducing animal food production could directly reduce 2 to 8 gigatons of CO2 equivalent emissions per year, methane, nitrous oxide, ongoing emissions for land clearing. What we found was a double climate dividend of being able to sequester an additional 3 to 8 gigatons of CO2 per year into regrowing ecosystems if we were to take on those dietary shifts. Those dietary shifts look very different depending on what countries you're talking about, and here are the sequestration potentials in those stacked colored bars next to the amount of fossil fuels that these countries at different tiers have emitted over the past decade. So in high and upper middle income countries, we're really talking about comparable amounts of sequestration that are around the past decade of emissions, sometimes less, sometimes even more. And that's where the majority of this mitigation or sequestration potential exists. We also modeled dietary scenarios out to the year 2050, both in a low yield and a high yield scenario on the left and right respectively. So this flips the convention from the other graph, where here positive is a bad thing. It means emissions to the atmosphere, and negative means sequestration into forests and soils. In both low and high yield scenarios, business as usual diets on the left of each chart result in positive emissions to the atmosphere because they require even further land expansion. In all scenarios, though, dietary change is likely to be a net sequesterer of carbon back into native ecosystems, predominantly forests. However, within a low yield scenario, even if we look to aggressive meat reductions in a healthy diet, while it's likely that this will be a net sequestration, within statistical uncertainty, we can't quite tell whether it still could result in additional land expansion. So there's a lot of kind of parameters that we varied to create these scenarios. So what this means is that the only guaranteed route to land sparing and the carbon sequestration that comes with it is both higher yields and shifts to very plant-rich diets. So findings from our and multiple other scenario analysis have all come to the same conclusion, that improving crop yields and animal production efficiency are both incredibly important. But these improvements, even when they're coupled with implementing next generation's emissions reduction technology like seaweeds and 3-NOP, will still be outpaced by rising demand for animal-sourced food by the year 2050. So the conclusion that I and many other researchers in climate and food systems have come to is that improving production and implementing sustainable consumption, which include plant-predominant diets and having food waste, are both required to meet 1.5 or even 2 degrees Celsius targets. So I think that's about the biggest picture that I can get you to, but there's still kind of a lot getting in the way of this conversation, including debates about which countries need to adopt these emissions, which types of systems need to adopt these emissions, especially when you consider that high-income countries are, despite the fact that we're eating more meat, on a per capita or per animal basis or per product of meat basis, sometimes emitting less, even far less, than rising emissions in developing countries. And our, what other thing was I going to say? Losing my thread here a little bit. Okay, are emitting less, and the emissions in high-income countries are more or less stable. We're not drastically changing the amount of meat we eat. We're consuming a lot of it, but it seems to be staying the same over time. Most of the growth in consumption is happening in high-income countries. And this has been leading to a lot of contestation about where the responsibility for most of the mitigation lies. You see this all the time as well in fossil fuel infrastructure, middle-income countries rapidly moving towards coal versus high-income countries having already burned it, now doing the transition. And we're seeing some of these debates play out again. So can we approach with a little bit more clarity where the methane emissions are coming from and how we can be really clear about what the opportunities to mitigate them are? First of all, we're going to talk about methane from more quote-unquote efficient, intensive animal operations. Many of you may not know that factory farming, despite having a lot of cruelty towards animals, actually emits less methane per unit of meat and milk produced than, say, production in South Asia or Sub-Saharan Africa, or a lot more agrarian production systems that are more extensive and pasture-based. And then we're going to move to talking some about alternative methane accounting metrics and some of the concessions that we can make for their accuracy, but ultimately why I think they end up failing. So first of all, this methane issue of methane from intensive operations. Because intensive producers frequently boast about their low and decreasing footprints, including the American Dairy Association, their New England chapter, saying that farmers have reduced the carbon footprint of a glass of milk from 2007 to 2017 by 19%. How do we know this? Well, we often end up knowing this by creating models of those production systems that account for a very complex number of parameters, including the population of those dairy cows, that's a variable there, parameters around how much activity they're performing, whether they're grazing or not, what types of consumption they're engaging in, how their manure is being stored, and even the climate that's affecting their bodies and their manure storage. Importantly, though, in this system, no methane is actually being measured anywhere in this model. So, and I think it's incredibly important that most of the measurements have either recently occurred in the past few years, or most of them have occurred in the past 30 to 40 years, or 30 to 40 years ago. And those parameters are what are calibrating these models. So it ultimately is an estimate that is not what we'd call grounded or constrained. So sometimes, if you want to get a larger view of emissions that were coming from a large area, you can measure it in the sky, from tall towers downwind, from airplanes up in the air, even from satellites. We can use satellites, airplanes, and tall towers and take a high-level measurement that is representative of a large area, but we don't want to lose too much certainty of where that greenhouse gas is coming from. And this is a really tough issue because you're only measuring from one or several locations, and you're only getting a fraction of the pollutants that are being emitted up to that receptor point, say in this case, up to the airplane. So instead, what you can do is you can take a measurement and try to follow those parcels of air back in time using a model like a weather research and forecasting model, in this case, WRF, and then using some statistics to take that model and go back in time with those air parcels, as well as some statistical likelihood of how much they're scattered in different areas, you can get some representative statistics backwards in time to the ground and understand where on the ground those pollution sources up to your airplane are coming from. In this example, it might be some small percentage from cows and some larger percentage from fossil fuel product. If another fossil fuel production, on another day, those ratios might tip in the other way and you're predominantly, majorly, or entirely emitting, or catching the emissions from those wind fields of predominantly animal agricultural production because the winds that day are blowing from a different direction. So we added up and we reviewed all of the emissions across multiple studies done before the year 2021 in a meta-analysis in environmental research letters. And we looked at multiple assessments, and more have come out since then, that say on a global level, these bottom-up models compared to the inverted measurements traced back to the ground using meteorological forecasting agreed with one another. The measurements and the models agree globally. But in the United States, when we compare these bottom-up models based on inventory methods, counting and modeling, to measurements that occurred in the atmosphere being traced back down in the wind field to the ground, the models consistently predicted less methane, or suggested there would be less methane than we actually ended up seeing in the atmosphere. In many cases, we saw 39 to 90% more emissions from U.S. animal agricultural operations, which are predominantly intensive. So what might they be missing? We have no clear answers. Again, this is based on real in situ measurements, but it has a very coarse resolution. We can't go down to the individual cow. But our hypotheses from more fine-scale measurements that have been done over the years include that we're under-predicting manure. And this explains part, but not all of it. There also seems to be something going on with the animal belches as well. It might be that the belches, the animals themselves, the operations have a non-symmetric distribution. And this is something that we've seen with fossil fuel extraction and methane leaks as well, that only 10% of operators are responsible for 50% or more of the methane leaks. Something similar could be happening with the animals. All of the models assume that there is an average Gaussian or just regression to the mean, but it may be an uneven distribution in real life. Overall animal numbers could be wrong as well, especially if young animals are dying before the census counts them. And the emissions intensity of modern diets and feeding rates might be underpredicted because farmers all over the country feed their animals entirely different feed baskets. It's not one representative diet everywhere. And this is incredibly important if we're looking at U.S. intensive operations, right? Because our style of animal management is currently being exported all across the world through levers of sustainable development and infrastructure, including pig hotels being constructed in southern China that have incredibly intensive monitoring and feed regimens for their pigs, and will be storing the manure underground in lagoons where it may be producing a lot of methane before it can be captured. So what we see is that methane from intensive animal operations are possibly higher than we've been led to believe. While they're still ultimately lower than those from extensive operations per unit of food productivity, the improvements from intensification might be smaller than previously thought. And this has major ramifications for how we're exporting these technologies and management methods all over the world. For example, by the year 2050, animal emissions from East and Southeast Asia production might be 20% higher than bottled-up models have previously predicted if we adjust those predictions by the type of scale factors that we found in our top-down analysis. So, We also have to look at the metrics that we use to compare methane to CO2 and compare one country to another, and make sure that we're counting that method and comparing it across greenhouse gases correctly. Because different greenhouse gases behave differently. CO2 sticks in the atmosphere for a long period of time, whereas the warming effect of methane disappears within a couple to a few decades. So a scale factor that integrates methane's warming across 100 years might be under-predicting its effect the year after you admitted it, and over-predicting its effect if you're looking at 100 or 1,000 years in the future. So we can instead use a metric that allows us to model the transient effects over time of a large pulse of methane to the atmosphere, or a constant or increasing or declining emissions. And this is something what that would look like. Here we see multiple global scenarios of emissions coming from smokestacks and cattle on the top, and the atmospheric concentration or its resulting warming, how it accumulates or doesn't in the atmosphere on the bottom. And while CO2 emissions accumulate in the atmosphere, CH4, methane, dissipates over time. So with linear growth in emissions here at the top, CO2 on the bottom grows more than linearly. If there's a constant emissions, however, of both gas, the CO2 will accumulate linearly, while the methane won't accumulate. The concentrations in the atmosphere and the warming it results in will stay the same. Meanwhile, if there's decreasing emissions to zero, CO2's warming and concentration will level off to a constant but positive amount over time, versus methane, the concentration and warming of methane will go to zero. In effect, the takeaway from this is that decreasing methane emissions can result in climate cooling. And GWP star, and it's a very confusing acronym, I didn't come up with it, as a metric or a global model, captures this well. This is a metric that was designed to. What is GWP star? It's a new metric proposed to create an accurate global model of temperatures responses to rising or falling methane emissions. If methane emissions come down gradually here, the rate of accumulation in the atmosphere here becomes negative. So while cumulative emissions, according to GWP 100 here, seem to go up, GWP star as a global model allows for the warming response of this gas to decrease in effect, and it does this accurately. Okay, so why don't we apply this to every single cow or smokestack or leaky well in the country? Well, as I said, GWP is an accurate global model, but it fails as an accurate or sensible way of dividing up the global emissions between different actors. Just because the global methane emissions coming down means atmospheric cooling, that doesn't mean that my sheep's emissions going down results in global cooling if other people's sheep are not going down, or if the opposite is happening, they're rising. We still need to look at how much those sheep are belching at one period in time. So, as an example, let's compare two countries with a hypothetical methane emissions and different trajectories of those emissions, but ending up at the same point before any conversion to CO2 equivalent happens, and ask how comfortable we are with the results from these two metrics. While GWP 100 looks at the amount right here, GWP star looks at the derivative or difference across the past 20 years here in this example year of 2010's emissions reporting. So now moving to another country, and let's click through. Now moving to another country, an example country 2, GWP 100 would again look at just the year 2010, while GWP star would look across those past 20 years across which there was no change, and would inaccurately come to the conclusion, I believe inaccurately, I think many of you would agree, come to a very confusing conclusion that country 2 was somehow responsible for zero emissions in the year 2010, while country 1 created all of the net warming in that year, if we could say somehow create a system where all the emissions were coming from two countries. Despite the fact that they actually emitted the same amount of real methane that year. And you don't just have to take a hypothetical example of this. Let's look at two countries, one with high but slightly falling emissions, and another country with low but significantly rising emissions. Australia in the former case and Kenya in the latter case. GWP star on the left suggests that Australia is responsible for marginal climate cooling in the year 2020 despite the fact that it emitted far more methane than Kenya did in that year. We can see, however, that GWP 100 creates more sensible answers. It just doesn't happen to fit neatly within that global model of those transient effects that we like to see. So if instead we divide that global model of GWP star up, that does produce those global effects that we like to see and that are part of a global, an accurate picture of how methane affects, we could use that as the basis for a new metric. And I and colleagues are just for now calling this GWA, or global warming alternative, as a metric, here on the right in a dotted line. And we can see that it comes to a far more sensible and less reprehensible conclusions while still doing what the original authors of GWP star intended, accurately reproducing the global temperature signal through modeling of emissions effects on concentrations, which is exactly what the GWP star authors are criticizing GWP 100 for not doing. Yet, in effect, as long as temperatures are still rising into the atmosphere, qualitatively they come to the exact same conclusion. So GWP star suggests that high-income countries' methane is essentially warming neutral, as long as their methane emissions, despite still being high, are level or even slightly decreasing over time. However, this is an artifact of the arbitrary and illogical methods that it uses to allocate global warming among different countries. What's good for the gander is not necessarily good for the geese. Production of emissions of meat and dairy are still high in high-income countries. So high-income countries are logically and mathematically still responsible for a large warming contribution as long as total methane in the atmosphere is still rising. And lastly, this gets me to the tricky business of emissions accounting and accountability, because many companies have been using science, that is scientific-sounding parlance, and incomplete accounting methods that only look at part of the warming equation to dodge what I'm calling the capital S science. Entire, skeptical, and systems-oriented scenario analysis that take all greenhouse gas sinks and sources into account. And many countries are beginning to follow suit, especially when they're falling privy, or when they are privy or easily kind of maneuvered around by the companies that hold a lot of influence in these countries, including by selling, quote, climate neutral products, some of which, or climate smart products, some of which the US government and other major governments have approved of labeling to go onto the market, despite being untrue or based on really shoddy accounting, making net zero or climate neutral commitments when they're livestock sectors and their food sectors as a whole have no trajectory of getting to be anywhere near zero, and false claims of emissions offsets and lobbying for further payment schemes to get those payments for only accounting for part of its sinks while neglecting some of the sources. We can see a number of products now coming out of the market that are carbon neutral, climate smart, etc., but using shoddy carbon accounting, offsets, and insets to get there. And consumers, to navigate this confusing environment, have to read fine print and look on websites. And often we find that the product itself is not climate neutral, it's relying on offsets. Sometimes even smoke and mirrors, like in the case of Woolmark and Australian Wool, saying that they're carbon neutral, despite not recognizing the fact that methane as a carbon molecule contains 20 to 80 times more warming than carbon dioxide as a warming molecule. There was no accounting for this in their carbon neutral scheme. In fact, they wanted to say it was carbon negative because your wool sweater somehow contains carbon that would otherwise be in the atmosphere. Yeah, it is carbon negative, but it's still creating warming. They're still belching methane and producing nitrous oxide. Using and lobbying for some of these erroneous yardsticks that provide a good global model but fail to attribute emissions responsibly, logically, or in a common sense way among different actors, which is exactly why the US Cattlemen's Association, as well as trade groups from New Zealand, Australia, and Ireland, are all lobbying their governments to adopt GWP star as an accounting method. and different kind of ways of dodging these issues, including back-to-nature puffery, pseudo-system science, again only including one part of the carbon equation, and miracle management that has unproven climate mitigation results, some even like Alan Savory and some more modern counterparts claiming that cows can somehow sequester so much carbon into grass and soils that they offset all of the nitrous oxide methane emissions from cattle into soils. When in fact, regenerative agriculture is unproven as a significant mitigation tool, or rather I will say meaningful mitigation tool, when the best evidence suggests that soil carbon removal has some potential but cannot offset more than a minor fraction of agriculture's, especially cattle's, emissions, let alone emissions from other industry like oil and natural gas. Yet we see even regenerative grazing researchers receiving millions from fast food and oil companies, and in the pitch for funding, claiming that this type of grazing will allow gas companies funding the research to sell gas as carbon neutral. Plain as day, this is on their own website. I didn't have to do a FOIA request for this. I think a nice salve to this is, again, my postdoc Shelby McClelland, as well as our colleague Mustafa, wrote a paper in Frontiers in Environment and Ecology and the Environment, which is a Wiley publication, noting the failure of carbon markets, this trading scheme for carbon in the soil, to include things like anthropogenic perturbations to the carbon cycle, like soil carbon debts of the history of carbon removals, rather than only looking at which current carbon markets currently do, only looking at the temporary sequestration that is happening in a given year that might be a coincidence of the land management over the past few years, and failing to acknowledge ongoing agricultural emissions, which in almost every single scenario vastly outweigh what sequestration might be happening in the soil, as well as mentioning that there are soil functions beyond productivity and profitability and major environmental justice implications of a lot of this money going to some of the top producers. So, to end on this note, industry collaboration with academia can gradually improve industry's production intensity, which is that productivity or that yield number that we need to come down marginally in order to stay within planetary limits, but cannot take us ultimately in the direction of the vast amount of mitigation that we need. We do need dietary change. We do need to reduce food loss and waste. And total emissions need external monitoring and guidance using skeptical, big picture, and systems-oriented science. I would argue that this last part, this bigger piece of the puzzle, cannot come from collaboration between academia and industry, as long as the goal of that collaboration is to prove that emissions reduction is working, because that's not how science works. Science only works by taking the most skeptical viewpoint and trying to falsify your hypothesis, not confirm it. And it's only through that skeptical system science that we can hope to identify and mitigate the largest emitting actors in the food system. And hopefully, with collaborations and diligent legal professionals and advocates, remove some of the barriers for rapid mitigation in the 21st century. And that's it.